Hi everyone, I'm Felix. Today I'm going to share how work flat and optimize data flow for mitigating attention bottleneck. This is a cooperation work with Google and Google Research. Attention-based model are important to Accelerate because there are more and more applications are starting to use attention model, and there are increased interest in longer sequence length. However, they are hard to accelerate because there are quadratic growth in complexity with this sequence length. And also the compute resources in the accelerator are often underutilized because of memory boundedness. And there are quadratic growth in memory footprint with sequence length. And the bottom two is the focus of this work. A quick recap of attention-based model. So attention-based model is essentially the combination of multiple of attention block. Each attention block, there are attention layer, normalization, fully connected, and so on. In each attention layer, there are query key value operator to project the input, and there are two attention operator larger than 10, and then do final output projection. Accelerator side, we have architecture and data flow. In architecture side, we care about two major resources, compute and buffer. In buffer, we have on-chip scratch pad and off-chip memory. On-chip scratch pad are often low capacity but high bandwidth. In data flow, we can do tiling and scheduling. Like tiling is how tensor slice, fetch, and store, and scheduling is how operator loops are ordered. And data flow is the focus of this work. So why attention layer is critical to be accelerated? Because if we develop deploy an end-to-end attention model to different platforms, we can see that attention layer consistently account for larger than 50% of the runtime. If we increase the sequence, then you can see attention layer just account for more and more runtime. And if you notice, the larger the 10, the yellow bar just contribute to the most of the runtime. So if attention layer is a very compute-heavy computation, why don't we just deploy it in an even larger GPU and TPU? Then we can solve the problem. Is it correct? So the problem is actually, even if you have a very powerful accelerator, you will still face a low performance issue because you will have low compute resource utilization. And we show this by a roofline model. And this is evaluated on TPU V3. You can see that many of the convolution operators will sit on the compute bound region, which is good. You can have the full opportunity to reuse their compute resources. Some of the fully connected operators are having low performance because of their memory boundedness. However, there are some easy trick. If we increase the batch size, then we can push them to the compute bound region. However, for the larger than 10 operator in the attention, even if we increase the batch size, pack more input, it still didn't help the performance at all. So what are we missing? So ideally, when we increase the batch size, we can improve the operation intensity and improve the performance. So let's see why it happens. So this is a standard fully connected operator. You can see that if we increase the batch size, we can have the potential to increase operation intensity. However, for a larger than 10 operator, the batch size are closed out. So algorithmically, our hands are tied. At this point, we propose to fuse larger than 10 operator together into one to open up new opportunity. So if you notice, we only mentioned we want to fuse larger than 10 operator. And however, in an entire network, there are a lot of different fusion operation opportunity as well. So fusion in this work, we only talk about tensor operation fusion. What I mean is that we fuse two tensor operator together, like convolution to convolution or Einstein sum to Einstein sum, like what we did for the larger than 10. And like also, there are some like convolution to fuse with batch norm or convolution fuse with add, which the current deep learning compiler are pretty decent at. So we will leave it. We will not discuss them in this talk. And in the attention layer, that are not only larger than 10, why don't we also fuse other tensor operation together? The key point is that they already have enough operation intensity without fusion. Here we show the operator inside attention layer, like a key query value output and other fully connected in the attention. We show with TPU V3, the minimum operation intensity to be in the compute bound region. You can see that all of the bar are passing the green line. So they already have enough operation intensity. However, larger than 10 sit here. So after fusing the larger than 10, we have the potential opportunity to cross this green bar and have the potential opportunity to fully utilize our computer resources. The second challenge is that larger than 10 operation will need large on-chip buffer requirement. Often to compute the operation efficiently, you want to stage the intermediate activation on chip. However, it is expensive. So at sequence length of 256, the intermediate activation of larger than 10 are 8.4 megabyte. However, when we increase to like 16K, it becomes 6.6 gigabytes for one intermediate activation. So it's very impractical in practice to stage all these big intermediate activation on chip. So at this point in this work, we optimize the data flow, which is tiling and scheduling in this work. What it essentially means is that we fetch partial of the input, compute partial of the intermediate activation, and compute partial of the output. Here we introduce FLAT. It's fused larger 10 tiling. The FLAT data flow composed of two parts, tiling and scheduling. So we also call it the basic unit of the flat data flow, flat tile. So why this flat tile is important? Because it respects the data dependency. So what I mean is that in larger 10, there's a softmax operation. And softmax is like row-wise softmax. So it means that it needs at least a row of data to compute the softmax correctly. So by this row of data, we can infer what's the least number of data we need from larger, what's the least number of data which can generate to the attempt to have a meaningful output. So this is the row granularity, the basic unit of flat tile. Also, on top of the row granularity, we can also have other parameterized flat tile and scheduling part. So there are cross operator scheduling. What I mean is that we in our scheduling we'll compute partial of larger and partial of a 10, partial of large, partial of 10 interleavingly. And also intra each operator inside larger, we can also decide which input-output weight stationary strategy we want to use. So as you can see, there are some very few hyperparameters that we can tweak on. So we can use a very simple design space exploration to optimize our performance evaluation. How we evaluate our model is that we do a progressive way. So what I mean is that we evaluate the larger 10 performance and attention block performance and the model-wise performance. And our performance modeling is public. The data flow we compare is first naive. Naive is just fixed tile size and schedule. And flex is that we use design space exploration to find the optimal data flow for it, just without flat fusion. And flat is that we use flat data flow with fusion, tiling, and scheduling. The performance metric is compute utilization. It's essentially ideal runtime divided by actual runtime. It's capturing the time ratio that compute is not idling for the memory. Here we look at sequence of 512, and we first look at a very large on-chip buffer size of 2 gigabytes. You can see that at very large on-chip buffer, no matter which data flow we use, we can often get very good compute utilization. However, when we start to decrease the buffer sizes, they become memory bounded, and the compute utilization just goes down. And if we compare flex with flat, we can see that for the larger 10 operation, flex, the optimal baseline needs 10 times more on-chip buffer to achieve close to 1.0 utilization than comparing to flat. However, model-wise, because they are amortized by other operator in the attention model, flex and flat are performing pretty similar. However, when we start to increase the sequence length, like maybe, for example, over 4K, then you can see that even for model-wise performance, flex, the optimal baseline, need 2 orders of magnitude more buffer to achieve similar performance to flat. And if we only focus on larger 10, flex is even need 4 orders of magnitude more buffer than flat. So here we are trying to show that flat can optimize the memory requirement for the on-chip buffer. So why is this important? Here we show an evaluation on on Tesla T4 GPU and using a dataset of protein sequencing, which often require long sequence. And the model we use is a BERT-based model with configured number of blocks. So if we can fit more blocks into the GPU, it means that we can build a deeper model and potentially have a more powerful model. So at the sequence level of 8K, you can see that naive baseline can fit in 3 blocks in the GPU, and flat can fit in 6 or even more. At sequence level of 16K, naive baseline cannot fit any block at all, while flat can fit in 5 blocks. We also see how flat can combine with state-of-the-art sparse technique, and the technique we consider is ELSA and Senga. The performance matrix of course, latency or runtime. And also we see their compute to memory ratio. When it's smaller than 1, it means that it's memory bound. First of all, we can see that both ELSA and Senga can very effectively reduce the latency of the comparing to dense baseline. However, if we add flat on top of ELSA and Senga, we can get extra benefit of the runtime reduction. So flat can further improve the runtime performance by around 1.7 times in average. Also, if you see this number that we show, it's the compute to memory ratio. So after ELSA and Senga, they are pretty much still memory bounded. But after we add flat on top of ELSA and Senga, they start to be close to 1 or even over 1. So we are moving from memory bounded to compute bound region, which essentially immediately eliminate the memory bottleneck. Also, we have flat prototype, which is also in public now. So the platform we evaluated is on Tesla T4 GPU, and we prototype the fused logic 10 operation, and we use JAX to prototype it. Here's the performance. At a sequence of 256, we want to see how big of the batch size we can fit on this GPU. So the naive baseline can fit the batch size to 128, while flat can fit up to 1K. And also the other experiment we did is if we fix the batch size to 1, we want to see how long of the sequence then we can fit. While naive baseline can fit 2K, flat can go to 64K, which is 32 times longer. Also, if you notice the runtime, flat has on average 1.5 times speed up over the baseline. Conclusion. The quadratic complexity of larger than 10 operation in attention layer causing 2 major issues. First is low performance because of memory boundedness. The second is large on-chip buffer requirement. And flat fuse larger than 10 operation and optimize the tailoring and scheduling, which increases operation intensity and reduces the on-chip buffer requirement. Overall, flat deliver 1.5 times speed up in our performance model across different model and different platform, and 1.7 times extra speed up on top of the benefit of ELSA and Senga, and 1.5 times speed up over the baseline in our JAX prototype, while also enabling 8 times larger batch size or 32 times larger sequence length. Thank you.